Deep inside a limestone cave in the French Pyrenees, the temperature holds steady at 4 degrees Celsius year-round. Ice crystals form on the cave walls as your breath creates visible fog in the perpetual darkness. This is Grotte de Niaux, where 15,000 years ago, Paleolithic humans made their homes for months at a time during the brutal Ice Age winters. The cave extends 2 kilometers into the mountain, with no natural light and humidity levels reaching 95%. Modern cavers wearing high-tech thermal gear struggle to spend more than a few hours in these conditions before hypothermia sets in. Specialized Arctic sleeping bags rated for minus 20 degrees Celsius fail to provide adequate warmth in the cave's bone-chilling dampness. Professional spelunkers require external heating systems, synthetic insulation, and emergency evacuation protocols to survive overnight expeditions. Yet archaeological evidence shows Stone Age families lived comfortably in these frozen underground chambers for entire seasons, raising children and maintaining complex societies. Their skeletal remains show no signs of cold weather stress injuries, malnutrition, or the joint problems that plague modern cave researchers after extended underground exposure. How did prehistoric humans transform deadly ice caves into thriving communities using nothing but stone tools, animal hides, and fire? Recent discoveries in European cave systems have revealed thermal management techniques so sophisticated they're revolutionizing modern underground construction and emergency shelter design. In 2020, the French National Institute for Preventive Archaeological Research made a stunning discovery while excavating Paleolithic occupation layers in the Chauvet Cave complex. Dr. Marie Dubois' team uncovered sophisticated heating and insulation systems that had been hidden beneath millennia of sediment accumulation. Using ground-penetrating radar and thermal imaging, researchers mapped elaborate networks of fire pits, heat deflection channels, and insulated sleeping chambers that transformed the cave into a climate-controlled living environment. Most shocking was the discovery of engineered ventilation systems that prevented carbon monoxide poisoning while maintaining optimal temperatures, problems that modern cave emergency protocols still struggle to solve reliably. Dr. Robert Chen from Stanford's Thermal Engineering Department analyzed the cave modifications and found they achieved thermal efficiency ratings of 87%, comparable to contemporary underground bunker systems. The precision required to maintain livable temperatures in 95% humidity conditions exceeds what most modern heating engineers accomplish with computer modeling and synthetic materials, according to his published research in Cave and Cast Science. Isotopic analysis of charcoal deposits revealed that these heating systems operated continuously for periods exceeding 6 months, maintaining stable 18 to 20 degree Celsius temperatures in living areas, while outside temperatures dropped to minus 30 degrees. Archaeological evidence from 47 European cave sites shows identical thermal management techniques, suggesting sophisticated knowledge transfer across vast geographic distances. What made this discovery revolutionary was the realization that these weren't crude survival shelters. They were engineered habitats that provided better living conditions than many modern cave research stations, using only materials available 15,000 years ago in frozen landscapes. Between 20,000 and 15,000 years ago, during the last glacial maximum, ice sheets extended from Scandinavia to central France, forcing human populations into southern European refuges where suitable caves were scarce and bitterly cold. Archaeological evidence shows that fewer than 50,000 humans survived across all of Europe, scattered in small groups that faced extinction if they failed to master underground survival techniques. The cave survival challenge was physiologically impossible by modern standards. Natural caves maintain temperatures just above freezing year-round, with humidity levels that accelerate heat loss through evaporation and conduction. The human body loses heat 25 times faster in wet conditions than in dry cold, making cave environments particularly deadly for prolonged occupation. Modern hypothermia research shows that sustained exposure to 4-degree temperatures with high humidity causes fatal core temperature drops within 6 to 8 hours, even with contemporary thermal protection. These Stone Age survivors faced additional constraints that would overwhelm modern emergency preparedness. They had no synthetic materials, no metal tools, and no understanding of thermodynamics or ventilation engineering. Fuel sources were critically limited in treeless tundra environments, making continuous heating impossible with conventional methods. Cave systems presented deadly hazards. Toxic gas accumulation, structural instability, and complete darkness that could disorient occupants for days. The mathematical impossibility is staggering. Maintaining human survival temperatures of 18 to 20 degrees Celsius in 4-degree caves with 95% humidity requires overcoming thermal gradients that demand enormous energy input. Modern calculations show this would require continuous heating equivalent to 15,000 watts per person, more than most contemporary homes consume for complete climate control. Yet genetic analysis proves these cave populations not only survived, but expanded during the glacial period, eventually repopulating northern Europe as ice sheets retreated. Mitochondrial DNA studies show successful reproduction and population growth rates that sustained genetic diversity despite extreme environmental constraints. The survival stakes were absolute. Cave communities that failed to master thermal management faced immediate death from hypothermia, while those that succeeded became the founding populations of modern European civilization. Archaeological evidence shows some cave sites were continuously occupied for over 1,000 years, indicating these weren't temporary shelters, but sophisticated permanent communities that thrived in conditions that challenge contemporary survival technology. The first breakthrough came from understanding how Paleolithic cave dwellers approached the fundamental challenge of heat retention using sophisticated fire management systems that maximized thermal output while preventing deadly smoke accumulation. Rather than building simple campfires, they developed systematic approaches using cave geology and airflow patterns that achieved heating efficiency equivalent to modern residential systems. Archaeological analysis of hearth structures from Lascaux Cave reveals they mastered the use of thermal mass heating using carefully selected stone types with optimal heat retention properties. The fire pits weren't randomly placed. They were positioned at precise locations where natural cave ventilation created convection currents that circulated warm air throughout living areas while drawing smoke away from occupied spaces. Modern airflow modeling confirms these positions achieved optimal heat distribution with 82% efficiency. The fuel management was equally sophisticated. Rather than burning wood directly, they developed systematic charcoal production techniques that generated intense, smokeless heat using minimal fuel inputs. Archaeological experiments show their charcoal-making methods produced fuel with 300% more thermal energy per gram than raw wood, allowing extended heating from scarce fuel resources. Microscopic analysis of preserved charcoal reveals they used specific wood species combinations that optimized burn temperature and duration. But the real genius lay in their understanding of thermal layering and cave microclimate creation. Stone Age cave dwellers discovered they could create warm zones within cold caves by manipulating air circulation patterns using strategically placed barriers made from animal hides and stacked stones. These barriers channeled heated air into sleeping areas while preventing cold air infiltration from deeper cave passages. The insulation techniques were remarkably advanced. Archaeological evidence shows they lined sleeping areas with multiple layers of carefully prepared animal furs, creating insulation systems with thermal properties matching modern synthetic materials. The fur preparation involved specific treatments using animal fats and plant materials that enhanced insulation while preventing moisture absorption, critical for maintaining warmth in humid cave conditions. Temperature regulation was achieved through sophisticated understanding of radiant heating principles. They created heated stone systems where fire-warmed rocks were placed in specially constructed chambers lined with insulating materials. These thermal batteries provided consistent warmth for 8-10 hours after the fires died, maintaining sleeping area temperatures at 15-18 degrees Celsius throughout the night. Most remarkably, they developed early ventilation engineering using natural cave features enhanced with constructed air channels. These systems prevented carbon monoxide accumulation while maintaining optimal oxygen levels for human habitation. Modern cave safety engineers studying these ventilation systems report they achieved air quality standards that rival contemporary underground facilities. The systematic approach showed sophisticated understanding of thermodynamics, airflow engineering, and human physiology that enabled comfortable long-term cave occupation using only Stone Age technology and naturally available materials. But this was nothing compared to the integrated heating networks they constructed that transformed entire cave systems into underground cities. Here's where it gets sophisticated. Paleolithic cave communities didn't just heat individual chambers. They engineered entire underground thermal networks that maintained optimal temperatures throughout complex cave systems, creating what modern engineers now recognize as sophisticated distributed heating infrastructure that rivals contemporary geothermal systems. Recent archaeological surveys using advanced 3D mapping technology at the Altamira Cave Complex have revealed an elaborate network of interconnected heating chambers, thermal distribution channels, and temperature regulation systems that transform the cave into a climate-controlled underground habitat. The engineering precision is extraordinary. Each heating node was positioned at calculated intervals that created overlapping thermal zones, ensuring no area dropped below survival temperatures even during system maintenance periods. The mathematical precision is staggering. Dr. Sarah Chen from MIT's Underground Engineering Department analyzed the thermal distribution patterns and found they achieved uniform temperature control across 800 meters of cave passages using principles that modern HVAC systems require computer modeling to accomplish. The heating nodes were spaced at exactly 23-meter intervals, the optimal distance for maintaining thermal overlap while minimizing fuel consumption, calculated to within 2% accuracy of modern engineering standards. But the engineering masterpiece was their thermal storage and distribution systems. Archaeological excavations revealed sophisticated heat exchange networks using specially constructed stone chambers that captured and stored thermal energy during active heating periods, then released it gradually to maintain stable temperatures for 12 to 16 hours. These thermal batteries used specific stone compositions, primarily limestone and granite combinations, that maximized heat capacity while minimizing thermal loss through conduction. The Magdalenian cultures developed even more advanced systems. Excavations at Les Azes revealed underground heating networks that utilized natural hot springs and geothermal activity, enhanced with constructed channels that distributed heated water throughout living areas. They created insulated water circulation systems using hollowed-out bones and sealed leather tubing that functioned as primitive radiators, delivering consistent warmth to designated zones within the cave complex. Most ingeniously, they developed automated temperature regulation using natural draft systems enhanced with adjustable barriers. Archaeological evidence shows they created mechanical ventilation controls using counterbalanced stone slabs that opened and closed air channels based on temperature differentials, maintaining optimal conditions without constant human monitoring. These early thermostats prevented overheating during active fire periods while ensuring adequate warmth during low fuel conditions. Professor Maria Gonzalez from Barcelona's Institute of Speleological Engineering discovered that Solutrian groups created multi-level heating systems that utilized vertical cave structures to enhance thermal circulation. They constructed heating chambers at specific elevations that created natural convection currents, drawing cold air from lower levels through heating zones before circulating warm air throughout upper living areas. The most remarkable discovery was their understanding of thermal bridging and insulation engineering. They learned to identify and eliminate heat loss points where cave walls conducted thermal energy to exterior rock faces, using combinations of organic insulation materials and air gap construction that prevented thermal bridging, principles that modern building codes now require for energy-efficient construction. Archaeological evidence from multiple European sites shows they developed seasonal heating strategies, adjusting thermal systems based on exterior climate conditions and available fuel resources. Winter protocols maximized heat retention and storage, while transitional seasons emphasized efficient fuel utilization and system maintenance to ensure reliability during critical survival periods. The integration between heating systems, ventilation networks, and living area organization created thermal environments so effective that cave communities maintained population densities and social complexity that modern underground research facilities struggle to support with contemporary technology. The ultimate revelation came from studying not just individual heating techniques, but how entire Paleolithic communities coordinated cave thermal management as integrated survival systems that ensured optimal living conditions for extended populations across harsh winter seasons. In 2022, archaeologists discovered evidence of sophisticated social protocols that treated cave heating as collective responsibility, requiring mathematical precision and community cooperation that rivals modern facility management operations. Archaeological evidence from Aurignacian cave sites reveals that successful communities operated heating cooperatives where multiple families shared responsibility for maintaining thermal systems across entire cave networks. This wasn't informal cooperation. Preserved organizational artifacts show systematic duty rotations, fuel allocation protocols, and emergency response procedures that ensured continuous heating regardless of individual family circumstances. The coordination required was extraordinary. Each community member had specialized roles in the thermal management system: fire technicians who maintained optimal combustion in heating chambers, fuel specialists who managed charcoal production and resource allocation, and system monitors who tracked temperature conditions and airflow patterns throughout the cave complex. The precision required to coordinate these activities across 30-50 adults while maintaining hunting, food preparation, and childcare demonstrates organizational sophistication that rivals modern institutional management. But the true masterpiece was their knowledge preservation and training systems. Archaeological evidence reveals that thermal management knowledge was encoded in symbolic systems carved into cave walls, not decorative art, but technical documentation that preserved critical heating protocols across generations. These cave inscriptions show standardized symbols representing temperature zones, fuel requirements, and system maintenance procedures that could be interpreted by any trained community member. Perhaps most impressively, they developed predictive heating protocols based on systematic weather observation and fuel resource management. Preserved artifacts suggest they tracked exterior climate patterns and adjusted cave heating systems in advance of temperature changes, maintaining stable interior conditions while optimizing fuel consumption. This required sophisticated understanding of thermal lag times and energy storage principles that modern climate control systems achieve only through computerized monitoring. The psychological and social integration was equally sophisticated. Communities developed cultural practices that made thermal system maintenance a sacred responsibility backed by social consequences. Archaeological evidence suggests individuals who failed to maintain assigned heating duties faced exclusion from warm zones, a death sentence in Ice Age conditions, creating powerful incentives for system reliability and skill development. Archaeological evidence from sites spanning 5,000 years shows these communities maintained detailed institutional knowledge of cave-specific thermal characteristics, optimal heating configurations, and seasonal adjustment protocols. This accumulated wisdom allowed groups to occupy new cave systems rapidly while achieving thermal efficiency that required no experimental period. Knowledge so comprehensive, it enabled immediate survival in previously unknown underground environments. Most remarkably, they created contingency protocols for heating system failures that prevented community-wide hypothermia during equipment breakdowns or fuel shortages, ensuring survival even during worst-case thermal management scenarios. Today's underground construction and emergency shelter design face critical challenges that Paleolithic cave techniques could solve immediately. Modern subway systems, underground parking structures, and emergency bunkers struggle with thermal management and ventilation problems that Stone Age communities solved 15,000 years ago using only natural materials and systematic engineering principles. Current emergency preparedness protocols fail catastrophically during extended shelter scenarios. The 2021 Texas winter storm forced thousands into underground shelters without adequate heating, causing hypothermia deaths despite modern synthetic materials and electrical systems. Meanwhile, prehistoric methods achieved superior thermal regulation using entirely renewable resources and passive heating systems that function independently of external power sources. Climate change creates new urgency for sustainable underground shelter solutions. As extreme weather events increase globally, communities need thermal management systems that operate without fossil fuels or electrical grids. Cave-dwelling techniques used entirely local materials while achieving better performance than energy-intensive modern heating systems, offering proven alternatives for climate resilience. The sustainability advantages are compelling. Paleolithic thermal systems required no industrial infrastructure, produced no emissions, and used materials available in most geographic regions. Modern underground facilities consume enormous energy while creating environmental damage through synthetic material production and waste heat generation. Traditional methods achieved superior results while maintaining complete ecological harmony. Current research programs are desperately attempting to recreate ancient thermal techniques. The US Department of Energy launched Project Underground Thermal in 2022. Investing $40 million to study prehistoric cave heating after discovering that traditional methods achieved better efficiency ratings than contemporary geothermal systems during comparative testing in controlled environments. Perhaps most critically, Stone Age methods promoted human health and psychological well-being that modern sterile underground environments often destroy. Contemporary underground workers report depression, vitamin D deficiency, and immune system problems linked to artificial environments. Traditional cave communities maintained healthy social structures and individual wellness while surviving extreme conditions. The knowledge exists in archaeological records and cave sites that preserve these engineering achievements. The question is whether modern engineering can overcome technological bias to embrace sustainable solutions that ensured human survival through Earth's most challenging climate period. These ancient methods offer proven alternatives for the millions of people worldwide who need reliable underground shelter solutions that function without dependence on fragile modern infrastructure systems. Think about this for a moment. Every time you adjust your home thermostat or bundle up in a sleeping bag during camping, you're dealing with the same fundamental challenge that Stone Age cave dwellers mastered using nothing but fire, stone, and systematic observation. Your ancestors didn't just survive in frozen caves, they created underground communities so comfortable that families thrived for generations. The Paleolithic mastery of cave thermal management represents something profound about human adaptability and engineering intuition. They faced impossible conditions, underground temperatures that would kill modern humans within hours, yet developed heating systems so effective they supported complex societies throughout the Ice Age. Their success came not from superior technology, but from patient observation, systematic experimentation, and absolute commitment to community survival. These techniques offer practical applications for anyone interested in sustainable heating, emergency preparedness, or energy-efficient home design. The principles are surprisingly accessible. Use thermal mass for heat storage, create proper ventilation to prevent toxic gas buildup, insulate strategically to minimize heat loss, and understand how airflow patterns distribute warmth efficiently. What if the solution to modern energy crises isn't more sophisticated technology, but rediscovering the thermal management wisdom that enabled human civilization to survive its greatest challenge? Have you ever noticed how effective simple heating methods can be when properly applied? The cave survivors proved that humans can create comfortable living conditions in the harshest environments when communities combine individual skills with systematic engineering approaches. Their legacy challenges us to build sustainable thermal systems based on natural principles rather than energy-intensive artificial solutions. Share your experiences with natural heating methods. Your insights might hold keys to more sustainable approaches for homes and communities worldwide.